I'm Neil Cotter with the University of Utah Electrical and Computer Engineering Department, and this presentation is called Filters, Fourier Series, and Overview. Let's consider the case of a cell phone. Suppose there was a single transmitter and a single receiver. Then it would be straightforward for us to sort out our signal from all the other many signals in the air. There are two good reasons to use sinusoids for our communication system. The first reason is that a sinusoid is a changing waveform that can create electromagnetic waves. A second reason is that we can build circuits that generate sinusoids quite naturally. In practice, there will be multiple people broadcasting at the same time, and we're going to want to isolate our particular signal from the others. Fortunately, the input to our cell phone may be treated as a linear sum of the input signals. This picture shows the composite signal for three sinusoids present at once. Our example shows the input as a summation of sinusoids, which might seem to be simplistic. However, Fourier's theory says that any waveform may be written as a unique sum of sinusoids, and we'll discover that there are other aspects of sinusoids that will make this a very powerful theory indeed. Getting back to our example, what we want to do is to extract the 600 megahertz signal out of the composite input signal, and that's where we use a filter. Here we show an ideal filter that is able to exactly extract just the 600 megahertz signal. An ideal filter would be able to exactly pass or completely block each frequency. Unfortunately, it is difficult to create an ideal filter with circuits. Here we show the output of a realistic filter. It's mostly 600 megahertz, but we have a little bit of 450 and 720 megahertz as well. Our realistic filter only partially passes or blocks each frequency. The good news is that it's easy to create filters with circuits. Now we consider how to design and analyze a realistic filter. One of the consequences of Fourier theory is that we can analyze what happens to each of the sinusoids in the input signal one at a time as they pass through the filter. After finding the output for each input frequency, we can use superposition to sum the responses. This sum is our output signal as shown above. The idea is that the signals coming in, the sinusoids, act as though they each are in their own channel, and we may analyze what happens in that channel separate from the other channels, then add up the results to get what happens when all signals are present at once at the input. Let's consider in more detail the process of analyzing each input sinusoid one at a time. Here we have the 450 megahertz input and output. And one of the remarkable things about sinusoids is that not only can all signals be represented as sinusoids, but when we put a sinusoid into a circuit, the output will be a sinusoid at that same frequency, perhaps with a different phase and magnitude, but it will be a sinusoid of that same frequency. Here we show an RLC bandpass filter that is set up to pass the 600 megahertz signal preferentially and reduce the 450 and 720 megahertz signals. As you can see, the output for the 450 megahertz is much reduced from the input. We use phasors for this analysis. For this RLC filter, the 600 megahertz signal passes through unchanged. In the design of the filter, the values of the inductor and capacitor are chosen so that in parallel, at a frequency of 600 megahertz, they act like an open circuit, allowing the input to pass to the output unchanged. Like the 450 megahertz signal, the 720 megahertz signal is much reduced at the output compared to the input. Notice that for each frequency, the output was the same frequency as the input. It was a sinusoid, but it does have a different magnitude and phase than the input. After we analyze the circuit using phasors, we convert the output phasors back into time domain signals. Then we can use superposition to add those time domain signals together to get the output signal. Note that we do not add phasors together because phasors change with the impedance of the L and the C in the circuit, and they are not compatible with one another if they are for different frequencies. It would be tedious to analyze every input frequency separately, but fortunately, we can usually analyze filters by retaining the frequency omega as a variable in the calculation and computing all the phasors at once. In summary, the tools we use to analyze and design a filter are Fourier theory, phasors, and superposition.